And so you have looked at what causes the emission spectrum, which is black background on colored line, and also the absorption spectrum, which is black lines on continuous background. So hopefully you understand the theory. Don't forget to pop in and make sure you watch the lecture video, and also the various application of our hydrogen spectrum. Okay, so we're going to focus on the past year question in this example discussion. And we are going to first read the question from summer 13 or May-June 13, paper 4.1. Grabbing my tablet. Let's go. The emission spectrum of the atomic hydrogen consists of a number of discrete wavelengths. All right. Explain how this observation leads to an understanding that there are discrete electron energy levels in an atom. So in this case, they are not asking you to explain the observation of the experiment. So you don't have to cover every single thing from when light passes through gas, blah, 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 blah. All right. They are just specifically asking for why does lambda, discrete lambda, brings to discrete energy level. Okay, so I think I'll start with lambda first. Okay, so I can say something that, for example, each discrete value of wavelength, which by the way corresponds to one color. Okay, so each discrete or specific value of wavelength, okay, corresponds or is associated to a discrete change in energy of the electron inside the hydrogen atom lah. All right, so that will be your first point. Because we have discrete energy transition or energy change, this shows that there's discrete wavelength. So the first mark, you should mention that this is a change in the energy of the electron. All right. And then the second point, you can say that the discrete energy change. What does the discrete energy change mean? It means that if let's say whenever there's an energy change, I always change these few fixed numbers only, it will mean that my levels are also the same few fixed numbers. Okay, so discrete energy change implies or means discrete energy levels, which you have answered lah. Okay, so if you find it a little bit hard to conceptualize this point, right? It is as if saying that, let's say you have energy levels. Okay, and to make my life easy, I'm just going to give them nicer numbers lah. Or not that the energy numbers are not nice right now. So let's say this is -1, this is -2, and this is -3. Okay, and what are the possible changes? For example, you could go from here to here, which is -1. Hang on, to make my life easy, I'm going to put this -4. Okay, you could go from here to here, which is -3, right? You could also go from, let's say, I don't know, what about here to here, you may ask. Can this will be -2. Can you have any other values in between? Let's say you go like, Miss, can I just change -0.5? This one is not allowed because you can only jump from one level to another level. If I repeat the experiment repeatedly, all I get is -1, -2, -3, -1, -2, -3. Then after a while, I'm like, okay lah. It means that the levels are discrete, not continuous. So think about you jumping down staircases. Your height is a discrete value from the ground versus you rolling down the inclined plane. Then your height will be a continuous value. So the energy levels are a lot like steps. So your height is discrete versus a continuous change in height with the inclined plane. Okay, so this is discrete. This is continuous. And from the photoelectric effect, we know that there's continuous properties. There's discrete properties of the photon. All right, so hopefully that will help you understand this point. Now let's move on to part B. Some electron energy levels in the atomic hydrogen is illustrated in figure 7.1. So you know that the electrons can travel in between these levels lah. All right, let's see. Longest wavelength produced as a result of electron transition between two of the energy levels. Okay, so they say for the longest wavelength L, draw and mark with the letter L the transition that give rise to this longest wavelength. Okay, let's take a moment and think about it. If your wavelength is longest, and from the equation, energy of photon is equal to hc over lambda. Correct? So if your lambda is the longest, this implies that the change in energy is the smallest. All right. So which levels where you jump, you got the smallest change one? Of course, it will be the narrowest energy level transition. This will be L. Make sure you label L. If you no label, then no mark L. Okay. You can draw anywhere on the diagram as long as you connect negative 0.54 to negative 0.85. Okay, next. Draw and mark with the letter S the transition with the shortest wavelength. Ooh, interesting. So shortest wavelength means the change in energy is greatest. You can see from this equation, when lambda is small, energy of photon is great. So we want the change in energy to be the greatest. We will transition from the highest energy level to the lowest energy level available to us in the diagram. Bloop. So this will be S for shortest. Can draw anywhere you want lah. Okay, as long as it's on the diagram. And the reason why I draw it downwards, okay, is because you are emitting, this give rise. So it sounds like emission to me. Emission of photon. Okay, so that's all. What other hints that you know that it is an emission of photon? I mean, here is another example. But you can see that you are you're producing this transition. So this is the photon that is being produced. Okay, many hints, enough now. So if your arrow is opposite direction, marks will be subtracted lah. All right. Okay, next. Calculate the wavelength of the transition that you show in part 2. Okay, part 2 is the shortest one, this one here. Okay, so I will take the transition from 3.4 to 0.54. Okay, I just need to find the magnitude or the difference. So I can say that the change in energy is equal to 3.4 minus 0.54. Okay, so you could find the change. If let's say this unsettles you, you could also write negative 3.4 minus negative 0.54, and then you omit the negative sign after that, because what we are looking for is just the change. All right, so think about the change, meaning we will take the difference between these two numbers. But this change in energy is hc over lambda. So this will be hc over lambda. I'm looking for lambda. I rearrange first. So h is 6.63 times 10 to the power of negative 34. Speed of light is 3.0 times 10 to the power of 8. And our change in energy here, I guess I'm just going to take the easy way out and take the bigger number, bigger magnitude, minus the smaller change, the magnitude, to find the change. Okay, if you get a negative sign, you should omit the negative sign after this. All right, because lambda cannot be negative. Okay, second point. Whenever I see E volt, I have to remind myself that this E volt have to change to joule. Okay, why does it have to change to joule? Because whenever you involve something like speed of light and Planck constant, all these VVIP in the physics world, These are SI units, meaning this thing also have to be SI unit. We need to convert 1.6 times 10 to the power of negative 19. Okay, so again, just a reminder, eVolt to Joule conversion. Come to here, multiply by electronic charge, travel back, divide by the electronic charge. All right, so now we're going to press our calculator and see what we get. 6.63, negative 34. Again, if you forget or you don't remember any of these constants, you can refer to the table of constants in the front page of your exam paper, the first few pages of your exam paper. All right, so I arrive at my lambda as 4.3465. So I guess I'm going to put 4.35 times 10 to the power of negative 7. Okay, so this wavelength always have to be in nanometer one. If your prefix is too off, negative 7, okay, let me scroll down here and show you. You see this one as negative 6. If your prefix is too far away from negative 6, negative 7, that means you done wrong liao. You didn't convert something, or maybe you misunderstand the question. Okay, so for the good thing about quantum physics is that you calculate stuff that you roughly know what the answer should be, the range should be. So if you cannot get something that is off that range, like this prefix, please check your working. This entire chapter is a bonus chapter. Struggle with electric field, don't know how to see magnetic flux change. It's a gift. Confirm you will use this equation one, just don't know which subtopic of quantum. All right, so let's move on to part C. Photo energies in the visible spectrum vary between 3.66 eVolt and 1.83 eVolt. Okay, to help us understand this, I have included the continuous spectrum. All right, so they say within the visible light vary from approximately 3.66, because everyone's eyes are different. Sometimes you say you can see the ray, and some people say like, what are you talking about? So we have the range of 3.66. 3.66 eVolt is high energy. Okay, so high energy is normally somewhere here one. Okay, and then low energy is, I don't know, I guess somewhere here. So high energy is purple, short wavelength, so this will be 3.66 eVolt, and the low energy here, red, will be 1.83 eVolt. Okay, so what are they asking us? They are saying that determine the energies of photon in the visible spectrum that are produced by the energy transition levels shown in this one. Wow, that's a lot of possibility, right? How many possible transitions do we have? So whenever we do with this kind of like possibility question, we have to have a system lah. You don't just randomly test energy level transition. Okay, so what you got to do is maybe you systematically test lor. Okay, we definitely have one transition already, which is S, and I guess L as well, but we'll start with S lah, the longest one. Okay, so from here I would say, or maybe I can draw a table. So the energy transition. Too bad they didn't label the shell. No n equal 1, n equal 2. So transition, okay, first one. I go from negative 0.54, sorry. Negative 0.54 eVolt to negative 3.4 eVolt. So the energy of photon will be the difference between these two numbers. Okay, so I think I write working one time lah. After that, no need to write already. 5.4. Why do I keep writing 5.4? 3.4 minus 0.54 eVolt, and this will give us 2.86 eVolt. Is this within this range? Yes. So if let's say 3.66 is here, they say emission spectrum, right? So 3.66 is here and 1.83 is here. So your 2.86 is probably the higher energy line. So maybe is this one? Maybe this one is 2.86 eVolt. Need to check actually, because you don't know which energy levels we're talking about. So we're just guessing lah. Okay. Next, transition. We will go slightly smaller. Okay, so what is the next largest transition? The next largest transition will be here to here. Bloop. No, actually, no, it's here to here. Ah, my bad. The whole thing. So the second transition will be negative 0.85 evolt to negative 3.4 evolt. So from here, the energy of photon will be the difference between these two numbers. 3.4 minus 0.85, 2.55. Still within range. So maybe 2.55 is this one. Okay. Third transition. What else? What is the next shortest one? Here. Lor. Bloop. So this will be negative 1.5 evolt to negative 3.4 evolt. So now the energy of photon will be 3.4 minus 1.5. Is it still within range? 1.9 evolt. So 1.9 feels like it's within range. Okay. So technically, right, I kind of don't know where these values are. Like, is it for the purple line? Is it for the green line? But 1.9 evolt is already quite uncomfortably close to the visible, the end of the visible spectrum already lah. So 1.9 is still somewhat, because it's quite close to 1.83 ma. So maybe this is 1.9 evolt. So maybe I need to fix the positioning of all this. If this is 1.9, then this will be 2.55 evolt possible. Okay, we need more information unless you convert this to wavelength. Okay, and maybe this one is 2.86 evolt. Miss, what happened to the other energy transition? Well, this is a hydrogen, right? This is actually not your lowest shell. There's still a 13.6 evolt that is not here. Okay, there you look back at your notes. There's still a 13.6 evolt here. We only started this one. Okay, so maybe there are certain transition here that is lost in translation, or maybe we don't know the colors. Okay, so I'm not going to fire up Google to find or double check the colors, but here you can actually tell that we are almost at the end of our rope, because what is the next shortest one? Let's say you want to test the next shortest one. This one, okay, which is, the whole thing here, 0.54 to negative 1.5. So let's test transition 4. Negative 0.54 evolt to negative 1.5 evolt. So what is this energy? The energy of this photon is equal to, 1 point, looks out liao, because it's 0 point something already. So this is 0.96 evolt, and then I can say this is out of range. Okay, so are there any more? Maybe, but based on the energy levels that are drawn to us, there is only these 3 possible answers. This one, and this one. So when you list down the photon energies here, right, you will say that this is 1.9 evolt, 2.55 evolt, 2.86 evolt. You could also be thinking, do I need to show the working? You should at least show the first 3 transition. Okay? Because if you don't, they'll be like, how do you get this reading? Okay? So this kind of roughly is able to roughly tell you what is the use of the hydrogen spectrum. Based on these numbers, we can actually know the energy level. Right, so out of curiosity, I went and do a bit of Googling, okay, and indeed, we can see that 1.9 evolt is around the red color, 2.55 is around green, and 2.86, actually 2.86 is close to violet. So you might be thinking, where is the missing energy level? I think the missing energy level is because there are some energy levels not drawn. Okay, and of course, color is continuous lah. Who gets to decide what color is what? All right. So here it will give you a good idea. Previously, whenever we talk about light, we talk about wavelength. But now you can also remember light have this thing called photon, and it has its specific energy that corresponds to the light that it has. This is extra added detail for you lah. Do you need to memorize? I hope not, because I have not seen questions like this before. What I have seen will be question where they ask you what are the energy transition possible. Okay, so go try out more past year questions. This is not the only one where they ask you about the possible energy transition. Go stare at some rainbows to feel good about yourself. And take care. I'll see you in the next one. If you find this helpful, please let us know what you think. Like, share, and subscribe. We'd like to hear from you, and I will see you then. Bye-bye.